So today we are going to start exploring what makes the quantum Hall effect possible. What allows for the precision of the effect, what makes the transitions happen, and so on. We are going to focus on two issues. The edges, pointing out that the edges must be gapless and chiral, and the bulk, focusing on the transitions between localization and delocalization and the essential role of each of the two sides of the transition. We have quantum Hall states with rho xy and sigma xy being in a plateau, and rho xx and sigma xx being 0. So the Hall resistivity rho xy is h over e squared nu. Rho xx is 0. And when you invert the matrix, you find that sigma xy would be minus e squared over h times nu, and sigma xx is 0. Minus signs are not so crucial here and are also not my strongest side. In any case, this is what happens in quantum Hall states. Now, in between two plateaus, as we see between any two plateaus like this one and this one, there are regions where sigma xy or rho xy are not quantized and sigma xx is non-zero. So those are the two aspects of this graph, and we'd like to understand them both. And to start with, we will start by thinking about sigma xx. Sigma xx is a measurement of a dissipation, right? Because sigma xx times Ex squared is the rate of dissipation. If sigma xx is 0, current flows with no dissipation. How come a current can flow with no dissipation? That requires the energy states at the chemical potential either to be absent, namely either to have an energy gap at the chemical potential, or to have states, but states which cannot dissipate energy, namely localized states. So the bulk of the sample here and here and at all the plateaus, the bulk of the sample should be localized or gapped. And at transitions between the two, where sigma xx is not 0, at transitions between two plateaus, where sigma xx is not 0, the bulk should be either gapless or delocalized. That's going to serve us later. But before seeing how, we need to say something about the edge. To say something about the edge, we need to look at the geometry where the edge plays an important role. So let us look at this geometry of a Hall bar. Imagine this going on to infinity in this direction. And imagine us putting an electric field parallel to the direction, or to the infinite direction of the bar. Now what's going to happen? We are in a quantum Hall states, and therefore if the electric field is in this direction, there will be a current perpendicular to the electric field. So there would be a current that would look like that, where negative charges go into one edge and positive charges go to the other edge. There's no dissipation associated with this current as long as it's in the bulk, because it's perpendicular to the electric field. But when it gets to the edge, it must find some states to occupy. And those states must be unoccupied. So they must be at the chemical potential. And they cannot be higher above the chemical potential because there's no supply of energy for those electrons or holes to go above an energy gap. So there must be gapless states, gapless edge states in this edge and in that edge as well. Now, if there are gapless edge modes and the electrons flow, now they flow parallel to the electric field. So they will absorb energy from the electric field. And for that absorption to have the right sign for the system to absorb energy from the electric field and not give energy to the electric field, there must be a chirality to the two edge modes, let's say with this direction for one of them and the opposite for the other. So you see, the edges, despite of the bulk being gapped or localized, the edges must have a different nature. Now, one thing you may wonder when you think about this is who cares about the edges? You know, the edges are just, in the thermodynamic limit, the edges are just a small part of the system. In fact, we can even imagine putting periodic boundary conditions, which would amount to putting the entire system on a cylinder, and then the edges become, there are no edges. So how come the edges seem to be important in this context? Let's see that. And let's see that by looking at two different geometries. One geometry would be this, again, the geometry of a bar, where we connect the two ends of the bar to two reservoirs at two chemical potentials. In this geometry, current indeed flows, as we saw before, along the edges, with one edge state going this way and the other edge state going this way. And if the chemical potential on this side is higher than the chemical potential on this side, there will be more current flowing along this edge than along that edge, and overall there would be current flowing from mu2 to mu1. This is a situation, a quantum Hall experiment, in which current flows primarily on the edge. But we can also have a different geometry where current cannot flow along the edge. And this is this geometry of a disk, where we apply an azimuthal electric field by changing the flux in a hole as a function of time. You know, by Faraday's law, if we change the flux as a function of time, we'll have an azimuthal electric field. And if the system is in a quantum Hall state, this azimuthal electric field will result in a radial current. So now the current will go through the bulk, and the edge seem to be completely irrelevant. So these two geometries are two different ways to measure the quantum Hall effect. They must give the same answer, even though one involves the edge in what seems like an essential way, and the other one doesn't care about the edge. Therefore, the same information about the physics of the quantum Hall state, or the same information about the quantization of sigma xy and about the vanishing of sigma xx and so on, must exist both at the edge and at the bulk. This is known in the context of topological states of matter as bulk-edge correspondence. And this is a concept that originates from the quantum Hall effect, but will show itself time and again in many other states, in many other points along this course. Now, the edge will be the subject of a different segment later on. And from now on, we will talk about the bulk. So to understand the physics of the bulk, or to analyze it a little bit more, let's start from how it looks classically. What would Aldude say about electrons in a magnetic field? Well, we know two expressions for sigma xx and for sigma xy. Sigma xx in Dude theory is n e squared tau over m times 1 over 1 plus omega c tau squared, while sigma xy is sigma xx times omega c tau. Now, here in these expressions, n is the electron density, E is the electron charge, tau is the mean free time between collisions of the electrons with impurities, m is the electron mass, omega c is the cyclotron frequency, EB times mc, where B is the magnetic field and C is the speed of light. Now, as a function of magnetic field, you see sigma xx goes down because of this factor, and sigma xy starts from 0 because, of course, at zero magnetic field, there is no Hall effect at all, and then goes up linear because of this factor omega c tau before it goes down because of this factor in sigma xx. Now, you know, classical physics in many cases gets the general picture correctly, but misses all the exciting parts. And this is exactly what's happening here. So let's now look at what quantum mechanics has to say about this. To start with, let's think about Landau levels. Landau levels have the spectrum that's linear in magnetic field. So the energy as a function of magnetic field is linear. which means that if you fix your chemical potential to some energy, you will find that in many regions, like here and like here and like here and like here and like here, and on, the chemical potential goes through a region where there's an energy gap. That goes well with what we said before. We need an energy gap or a set of localized states in order to see the quantum Hall effect. Now, let's put in this order and try to understand what happens to the issue of localization or delocalization when are states at the chemical potential localized and when they are not. So let's look at high magnetic fields first. At high magnetic fields, basically each Landau level is well separated from the other Landau levels. And therefore, the physics of each Landau level does not involve any mixing with other Landau levels. Now, below the energy of the Landau level, well below, we are in a gap, and we would expect that if there are states there, they are localized. So here, for example, at below the lowest Landau level, we would have sigma xy quantized to 0. And above the first Landau level, we would have sigma xy quantized to 1. 1 in units of e squared over h, of course. And next to 2, and so on. Now, in order to go from 1 to 2, in order to have a transition, as we said before, sigma xs will become non-zero, and therefore the chemical potential must have delocalized states. So somewhere in the Landau level, somewhere at the, close to the original energy of the Landau level before we put in this order, there will be a set of delocalized states that will go from one side of the sample to the other side of the sample. That will happen here, that will happen here, that will happen there, and so on. What would happen as we make the magnetic field weaker? First of all, one thing is not going to happen, and this is that those lines where there are delocalized states would stop existing at some energy. You cannot have no delocalized states in between this region of quantized Hall state with a sigma xy equals 0 and this region with sigma xy equals 1. There must be delocalized states in order to allow for a transition. So this line of delocalized states must continue as we go to weaker fields. Where would it continue to? Well, to understand that, we need to add another piece of information. And this is what happens at zero magnetic field. At the line of a zero magnetic field, we know from Anderson's theory of localization, from the original theory of Anderson and the following theory of the gang of four, we know that there would be no delocalized states along this line at all. All states at all energies for zero magnetic field are localized, which means that those states from here, those lines of delocalized states, cannot touch the line of zero magnetic field. So what would they do? The only choice they have is to, or the only sensible choice they have is to climb up to infinity. And therefore, the lines of delocalized states would start at overlapping with the lines of Landau levels. But as magnetic field gets weaker and as the omega c becomes weaker than the energy scale of the disorder, the lines of the localized states must climb up. This is a zoom in on the same picture. Now let's imagine what happens if we fix the chemical potential and we ask what does the Hall conductivity do as a function of magnetic field. So let's fix the chemical potential and start going from zero magnetic field and see what happens to the Hall conductivity. Well, here at the very weak magnetic fields, you see that this region is connected to this region, where sigma xy was 0. So here, it's hard to write, but sigma xy will be 0. This region here is connected to this one, where sigma xy is 1. All this, again, in units of e squared over h. And this is connected to this, where it's 2, and this is 3. And then this one, as I make the magnetic field stronger, I go from 3 now to 2. and to 1, and eventually outside of the board back to 0. So the whole conductivity, as I increase the magnetic field, starts from 0, then goes up, 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 and then start going down. That's exactly what classical physics told us, that it first goes up and then goes down. What classical physics missed was that this climbing and descending goes not smoothly, but in steps. Those steps, which are the quantum Hall effect, are an essential consequence of localization, which is exactly what Drude theory missed in the present context. So what we saw in this segment was the essential aspects needed for understanding of the quantum Hall effect. We saw the bulk being localized in quantum Hall states and delocalized at transitions. We saw the edges having gapless and chiral modes flowing in opposite directions at the two edges. And we saw how those two combined together to explain the existence of quantum Hall states and of transitions between quantum Hall states. Now we focused most of our discussion on Landau levels, and in fact on Landau levels of non-relativistic electrons. But this is not crucial. Those aspects, localization, delocalization, chiral edge modes, are going to be applicable to quantum Hall states in a much broader context. Also for the fractional quantum Hall effect, also for integer quantum Hall effect in beyond the context of non-relativistic electrons. And we will see that later on in many places in the course. In the next segment, we will add the fractional quantum Hall effect to the picture and see what unique aspects of the fractional quantum Hall effect come into play.